sweating on like crazy, I have to take my jacket off. Alrighty. Alright, do I have everything? Sorry, Jean. Okay, well, I hope Kayla is alright. It's not like her not to join us. I'm going to get started. Hopefully she'll jump in. Okay. Alright, so chapter 14, we skipped chapter 13. Some of this information in chapter 14 is linked to some of the developmental issues in chapter 13, so I'll try to highlight those where I can. I really like this chapter actually. It's looking at how do we connect our perceptions of the environment with our action, with our movements. And also we will look at, so today we'll look at that, and then on, what day is today? Tuesday, Thursday, we'll look at how we control our posture and our balance. And hopefully we'll also start chapter 15 on Thursday as well, otherwise I'm going to get a bit behind. So we'll see how this goes with that new schedule. Okay, so it's probably not going to be new news for you, given that we've been talking about our triangle and this interrelationship between the three types of constraints, but also that our developmental systems are interrelated as well. So what we think, and it has changed over the last 30 years or so, as we're learning more about the brain, right? That we think that movement and perceptual development, so things like depth perception, or perception of shapes, or the perception of three-dimensional objects, that those are related quite tightly. That the more I move, the more I understand the environment and how it's set up. So we have to be able to move to start coupling, and that fancy term coupling just means linking the perceptions and the movements and then being able to fine-tune them. So, I think I mentioned earlier in the semester that back in the late 50s and early 60s, researchers were looking at perceptual motor programs as an opportunity to rehab learning difficulties in the classroom. That really didn't pan out. It didn't end up getting a lot of support. But that doesn't mean that perceptual motor activities aren't important. So things like, things that I do on the playground, like walking along the beam or walking over the stepping stones, or getting the children to match colours when they're balancing, for example. Match the colour of the beanbag to the balancing pod that you're on, or match the jumping sack to the color of the cone that you're going to throw the ball at, things like that. Those are perceptual motor activities, all right? So these activities, it's still believed, are really important because they give children more experience at connecting these two. You know, it's probably not conscious a lot of the time, but the brain is learning to take in this sensory information, right? Because perceiving the environment is all about that sensory. What can I touch? What does it feel like? What do I see? What do I hear? Right? To a lesser extent, what do I smell? Okay? So they give children a lot more experience at connecting these concepts, and that gives the children more confidence in their movement skills. Okay? And we can, in our movement programs, we can reinforce concepts like shapes, directions, up, down, spatial awareness. Am I going over or under the barrier, right? And these are important tools for the classroom teacher. So I think it's one of the arguments that we need to start making from a theoretical standpoint, right? We need to say we have theory, we have research, we have real science that says we can help you in the classroom. Don't cut PE, don't cut recess, right? Moving is as important as learning to read and learning their numbers, because I can do that within my movement program, right? We've got to get them on board because we're losing the fight. So with the development of really clever brain scanning equipment, we're learning since late 1990s, maybe early 2000s, we've learned an awful lot about the relationship between the area of the brain that controls movement and different areas of the brain that are involved in cognitive awareness. And when we exercise, we see an increase in a substance called BDNF. That stands for brain-derived neurotrophic factor. So it's way easier just to call it BDNF, all right? But BDNF stimulates the growth of neurons within the brain, and particularly the synapses, so the wiring, the talking between the neurons, right? And it also protects against the loss of neurons. So one of the really interesting, if you go right to the other end of the lifespan, people who are interested in working with the elderly are starting to find that the more exercise they do, the better their cognitive awareness, the better their memory is, right? Because they think, because of this increase in proteins and hormones within the brain when we exercise. We also see an increase in growth factors that are hormones that work together with BDNF and stimulate capillary growth in the brain. So more capillary growth means that I'm getting more oxygen and more glucose to the brain to maintain function, right? So it's a really fascinating area of research right now at either end of the lifespan, okay? It looks very much as though there are certain areas. There she is. Hi, Kayla.
Sorry, I'm late.
That's okay. I was late starting as well. So it looks very much with these brain scans that we can do now that there are areas of the brain where we are thinking and planning, and areas of the brain that are sending out motor signals that are in the same kind of, in the same vicinity within the brain, right? So they're very, very easy to talk to each other and be connected. There's been a lot of research, particularly, and it's ongoing. So this particular meta-analysis, I think, was, I think this was 2013, but there's been a lot more research since then, but I don't know if there's another literature review since then. Looking at studies, again, the people who are involved in movement, so the motor behaviorists, the PE teachers, are really, really trying to persuade the education departments, both federally and at state level, that they should not be cutting PE and recess, right? Not just from a physical health perspective, because that argument didn't work, right? People are still cutting PE and recess, even though we know that that increases the chance that these children will become overweight and obese. So they're taking a different approach. They're trying to make the argument that movement significantly impacts cognitive functioning. So what they're seeing is that for a period of time after a movement program, whether that's PE or running around on the playground at recess, what they see is increased levels of attention and learning in the classroom, right? For an hour, 2 hours, but that's an hour that the children wouldn't have been paying attention and learning new skills if they hadn't gone out and run around for half an hour, right? So it's really important work, I think. And there is clearly a positive relationship between physical activity of a certain, I think probably it has to be at least moderate levels of intensity, and cognitive functioning, right? So that's an important key for classroom teachers, right? Don't fight for more time in the classroom. Fight for PE and recess, because it will help your time in the classroom, right? So when we look at infants, it's relatively obvious that some forms of perception to some level of development occur before we see the real voluntary movement and self-locomotion. So, we know they can see at a certain level. We know they can hear. We know that they're touching and playing with toys, right? So it's not a big stretch to say that some level of perception is developed before they start to move with, and really movement here means self-locomotion, all right? And that these movement skills then are acquired with that guidance. So it's, the child starts to get interested in what is that object. I can see that object, or I can hear that object, but I can't get to that object, and that drives the development of self-locomotion. Then, once we've got these actions, once we've got these movements, then we learn new perceptions about the environment, right? So I don't know if you know this classroom, but if I'm standing right here by the camera, I don't know that outside that door leads to a corridor that leads to the outside, right? It would be feasible to think that that door leads outside, right? I have to move and get a different sense of sensory information to know that there's a corridor before I get outside. Does that make sense? Right, and that's a kind of simplistic example, but that's exactly what infants and toddlers are doing. That's what their brains are learning about the environment, right? And so we know that exercise is stimulating activity in areas of the brain that facilitates learning and memory, right? So that's going to have a huge impact if we can just get the classroom teachers to buy in to these ideas, right? Means either they'll help us keep PE in recess, but also maybe they won't have the children sitting down in class for a whole hour. Perhaps they'll start incorporating some movement breaks or even movement activities that that incorporate the content they're trying to do. Or maybe we get rid of chairs in a classroom and have yoga balls, or only have standing desks, right? There's all kinds of things we could do in the classroom that would help children's learning and attention span, right? We just don't do it. We buy more tables and more chairs, okay? So I wouldn't have any chairs in this classroom if someone gave me the money. I have like 4 yoga balls. I wouldn't have any chairs at all. I'd only have yoga balls. The chairs are silly anyway, right? They're only one size. What if you're a 6'5", 350-pound linebacker? You don't even fit in the chair. Right? So balls are a better idea all round, in my view. But anyway, no one listens to me. They should. Okay, so let me just run back here and do a segue here. So we've got this connection then between sensory perceptual information and movement. And this is an old study, and I think that they interpreted the information from this study slightly differently back when it was originally run. But now we can look at this data and put a different interpretation, slightly different interpretation on it. All right, so what they did with this initial study was with kittens, and they had the kittens on like merry-go-round in a drum, and one kitten was walking and making the merry-go-round turn, and the other kitten got a free ride, and it was sitting in a little crate, and it was going round and round, but it got to sit down. So what's interesting about this piece of data is that both kittens were getting exactly the same visual information, right? They're both going round and round and round and round and round, and they're looking at the walls, right? And they're seeing exactly the same thing. One of them is moving, one of them isn't moving. What they found was that at the end of the study, that the kitten who was stationary, who was sitting in the little box or basket, had quite significantly delayed motor skills compared to the other kitten, and also its depth perception was delayed because it had got that visual information, but it hadn't been able to couple it with the walking pattern. So, fascinating study, I think. Move forwards 20 plus years, actually, I'm going to show you a little bit of video first before we look at this. She says, hopefully, we will look at a little bit of video. So, this experiment on this video is actually discussed in more detail in the previous chapter, but it relates very closely to the next piece of research that we're going to look at. So I wanted to show you this. And I have to find the right piece of film because this is too long.
Or pattern surface right under the glass. Other side of the table, the pattern surface is way down on the floor. So visually, it looks like a big 3-foot drop-off. So when human babies first begin crawling, most of them will crawl over the apparent drop-off, but after several weeks of crawling experience, then they'll begin to refuse to crawl over the drop. And the conventional interpretation of this was that infants are avoiding the drop-off because they're afraid of pain.
Backing away. She's not sister. She must look like that.
The experiment became the shaky foundation of a myth that crawling innately teaches us to fear heights.
Babies avoid going over the drop-off because they're afraid of heights. How do we know they're afraid of heights? Because they avoid going over the drop-off. So as you may have noticed, the argument is circular.
As it happened, the visual clip was a better test of an infant's depth perception, not their fear of heights. And if you look closely, you may have actually noticed that the babies don't look particularly scared.
It is a perfectly safe surface of support. So after one trial, human infants cleverly figure this out, and then they will crawl over the drop-off.
So how do you really test if a baby's scared of heights?
You can test babies at the edge of a real cliff where there's no safety glass. It's just an actual drop-off. The drop-off can be adjustable, so it can be little or really, really big.
And why stop there? Inside Dr. Adolph's infant action lab, babies are tested on a variety of apparatuses.
You can test babies at the edge of the slope, so it can be steeper, crossing bridges that are wide or narrow over a surface of support, and so on. If there's no safety glass, you can test the same baby dozens and dozens of trials in the same session. And that means that you can determine for each individual
Watch this angle.
that surface is safe.
Watch what happens at the point it gets.
Of accuracy.
Oh look, I'm not going down there face first.
Everyone has spent 25 years running tests like these, and the resulting data sets are both convincing and adorable.
Infants spend most of each trial right at the edge of the precipice. They're reaching their arm down over the drop-off. They are putting their little feet or their little hands on the bridge and taking little tiny steps at the edge. And all the while they're doing it with either neutral or positive facial expressions.
What's more surprising is how their approach changes as they learn different forms of locomotion.
So what happens is that when babies first begin crawling, they'll crawl right over the edge. Then over weeks of crawling, their responses get more and more accurate until finally they're at adult-like levels, so that they can tell precisely whether a slope is safe for crawling or whether a drop-off is safe for crawling. But then the next week, when these babies stand up and face these same drop-offs, same slopes, same apparatus, now it's a new walker. They walk right over the edge. So in fact, there seems to be 4 learning curves in development as babies learn to sit, learn to crawl, as they learn to cruise, and then finally as they learn to walk. So,
All right. I would highly recommend you watch that whole piece of film. It's really interesting. But that gave us enough for me to talk to you about. So let me just run through what those experiments were showing again, because the volume, the sound's a little bit mushy on that piece of video. So what they have found is that so they get a population of infants pre-creeping, pre-self-locomoting, right? And they monitor them, and as soon as they start to self-locomote, creep, the parents bring them into the lab. So that first week of self-locomotion. And I haven't seen anything where they include the crawling, like the belly crawl. They seem to wait until they're on hands and knees. But that first week of creeping on their hands and knees, they put the baby on the checkerboard, and it will creep, and mum is the other side of the table with a toy, and it will just go straight across the visual drop-off without even noticing that it's there. So they film that. Baby goes home. Mum brings baby back 2 or 3 weeks later. So now this infant has 3, maybe 4 weeks worth of creeping experience, okay? And now what they find is that they put the baby on the checkerboard, mum's standing there with the toy, baby starts creeping, gets to the edge and goes, whoa! And looks at mum and looks at the edge and looks at mum. It isn't a real edge in the visual cliff experiments. They've got glass there, right? But still, this child that 2-3 weeks ago was happy to crawl straight across, had no awareness that there was a drop-off, right? Now, with that movement experience, the brain has learned some depth perception, okay? So depth perception, 2 dimensions, 3 dimensions, all these things that we take for granted as adults has to be learned by the brain, right? We're not born with that concept. The brain has to learn that idea, okay? Keep in your mind the picture of the baby going up and down the slope, because we'll come back to that idea in a minute. This piece of research is really fascinating, because what they did here, and this was in the mid-late 80s, over in, I think they're in Campos's lab was over in California, San Diego, maybe, can't remember. And what they did was they wanted to really identify that it was the self-locomotion experience that drove this depth perception development. And so what they did was they took the pre-locomoting babies and put them into baby walkers so that they could self-locomote, okay? So they took the pre-creepers, put them into baby walkers, and these children that weren't yet self-locomoting could now self-locomote. And so then what they found was that if you put this infant onto the visual cliff, it stops at the edge, right? So it's the locomotor experience, not the age or the, if we go back to that idea of the maturation theory, it's not the maturation of the sensory system or the visual system or whatever. It's the locomotor experience that drives the development of depth perception. So, fascinating piece of research, I think. Okay? Any questions? No? Okay. So, I'm not going to spend time on this first study on this slide. You can read about this one. They were looking at how much movement experience did it take to get a child to go around a barrier to pick up a toy. So they were looking a little bit at spatial perception and object permanence. So if I take a toy and I shake it and then I put it behind a sheet, does the baby creep around to the edge of the sheet to see the toy? right? Do they understand that there's a behind the sheet? So it was when I read this study, to me it seems like a bit of a combination between they understand object permanence, but they don't understand that there's a behind, right? That takes locomotor experience again. The second study here, Gibson, again in the late 80s, was the study that drove Dr. Adolph's, but her lab is a lot more sophisticated than the original study was. So they were looking at this idea of slope and surfaces, okay? So if you remember in that piece of film, they had a sophisticated setup where they could change the slope by turning a handle, right? And that baby was, again, with experience, it will, without experience, it will head first down that slope regardless of the steepness, right? The more experience they have with creeping, and you saw it, right? She would go down, she would go down, she would go down, and then they turned it one more bit, and she went, whoa, no, I'm going down backwards, right? So that creeping, that self-locomotion, gave her the understanding that that last slope was too steep to go down head first. She needed to turn around and go down backwards. Then what happens, that baby then, a week later, 2 weeks later, stands up and starts walking on its own. They put them at the top of the slope, they just go straight down again. And it takes a week or so of walking for them to get to the point where they go down, they go, yeah, no, and they turn around and go down backwards. Right? So the change, what I think is happening is the change in the head position and the height from the floor. Then the brain has to relearn the steepness of the slope and the depth perception. Right? So a new walker goes back to something that's unsafe for a week or so until they've got the experience to couple that new sensory information with their walking pattern. Okay, so quite a while ago now, we talked about this idea of affordances, right? And the affordance is the opportunity for movement that is afforded by the environment I can perceive, right? And it's strongly tied to my understanding of my capabilities. Maybe not consciously tied to my understanding of my capabilities, but it's my brain is tying it in, right? So from an ecological umbrella, right, if we're looking at ecological theories, that they would say that we perceive that affordance. I don't necessarily have to recognize, and compute what's going on in the environment. So what's that environment going to permit me to do as an individual, right? I don't have to analyze the things that are in the environment. That would be an information processing approach, okay? So a really good example of this is climbing upstairs in your house, all right? And in this part of the country, there aren't a lot of houses that have an upstairs, so I don't know how easy this is for you to visualize. But I grew up in a house where you went upstairs to bed, right? And what you see, if you ignore the research for the moment, you can just see this for yourself, right? If you've got an infant that is just standing up, right? Or even 18 months old and starting to run, the typical stair height in a house isn't manageable for that infant. So when you watch them go up the stairs, they'll either stop walking and drop down onto their hands and knees and go up on their hands and knees. Or if they're a little bit older, then they might hold on to something and go up sideways like 1 foot and then lift the other foot up and then take another step, right? Either holding on to mum or holding on to a handrail, perhaps, right? It takes quite a long time before you see this child look at the same set of stairs and go up 1 foot at a time forwards, right? Over that individual's lifespan, it's going to keep going. I mean, it's, you know, unless you're carrying something really heavy, constraint, right? Most of the time, we go upstairs 1 foot at a time as adults. Until, what? When might I stop going upstairs 1 foot at a time as an adult? Think of a context where you might see an adult not go up 1 foot at a time.
When they start to run, maybe?
I'm not sure what you're trying to say there. When the adult is running,
Yes, once you pick up the skill of running, is that when you stop climbing the stairs one at a time?
no, you're thinking of children though. I'm thinking adult, right? So you're in your early 20s. For the next 20, 30 years, you're going to go up the stairs 1 foot at a time. Probably. Right? Unless, as I said, you've got a task or an environmental constraint. What if the stairs are icy? Do I go up 1 foot at a time then?
Or you're in a rush?
Or you're in a rush, right? Or are carrying a big load of laundry. Okay, so there are situations with environmental or task constraints that would even change your climbing pattern, right? A few years ago, I guess, I've been here too long, must be 8 years ago now, 7 or 8 years ago, we had a pretty bad snowstorm and ice storm in Portales, and those of us in the HPE department had offices still in Greyhound Arena, but we had meetings and things on the other side of the road on main campus. And it was, you took your life into your hands to climb over the footbridge to go to your meeting, right? There was this big argument between the university and the city as to whose job it was to salt the steps over the footbridge. So you had to give yourself like an extra 10 minutes to get to a meeting so that you could climb up the stairs really carefully and get across the bridge, right? What about as we get older, right? What if I'm in my 70s or my 80s? What might you see?
When you climb the stairs and you're not going one at a time anymore, but you're like taking 1 foot onto a step putting the other one next to it, so you
Exactly.
climb much slower.
There you go, right? So the movement pattern changes back to something we saw infants and toddlers doing, because now could be any number of individual constraints. It could be leg strength. It could be hip mobility or knee mobility because of arthritis. It could be a functional constraint, fear of falling, right? So this person who's gone up this flight of stairs their whole life suddenly starts going up these stairs a little more cautiously, right? So stairs afford, the stairs didn't change, right? The environment didn't change in the house, right? The affordance, the opportunity to move changed because of the individual's perception of their capabilities, right? So one study that I think is quite interesting, although it doesn't, you can't generalize it, unfortunately. But this researcher, Warren, found that in adults, the adults would walk 1 foot at a time up until the stair rise was around 88% of their leg length. And once it went to 90%, they stopped and they climbed up, and then they climbed up again. Right? Unfortunately, that model didn't translate to what they saw in an elderly population. The point at which they transitioned from single stepping to one-footed stepping was more connected to the strength of their legs and their flexibility in their joints. And it also didn't translate to infants and toddlers, although they will choose to go up 1 foot or 1 foot at a time or single stepping, depending on the height of the stair, but it didn't relate to this ratio to their leg length, unfortunately. But it was really interesting. Okay. So then we move away from the studies and the research on self-locomotion, and we start to look on at the idea and the development of using toys, tools to achieve a task. So with infants, it's very much trial and error. They don't pick something up and straight away put it in. You know, I said a few weeks ago that around the first birthday, that's a good time to buy those toys where you've got different shape holes and different shape pieces that fit in the holes, right? Initially, they're gonna just try to jam the wrong size, the wrong shape piece into the wrong hole, right? It's very much trial and error. And then the more they do that, right, the more they practice, then they start to relate the objects. So remember our haptic perception, right? What shape is this object, right? Which hole does it fit in? Okay, so they start to be able to relate the haptic information about the object with the visual information about the shape of the hole, right? And that haptic perception develops in a certain order. So they do the manipulation to learn size and temperature first. Then they start to learn texture and hardness with the prodding. And then they learn weight and shape with the feeling. So that manipulation and that understanding proceed together. So you've got a movement, action, and the cognitive understanding of the shape of that object or the weight of that object are developing together in a certain order, right? And so that affects these games and toys, right? So again, we have a slight difference between ecological theories that would say it's the relationship between the tool and the surface that affords the movement, right? They learn that affordance rather than an advancement in cognitive ability, which would have been maturation theory. So, learning to move my arms, remember my proximodistal development, right? Starting to get better control of my arms and my wrists and my hands and my fingers also facilitates perceptual development. Okay? They're all tied together is really the big picture, right? Where we are right now in the research is that all of these things develop together. And if we withhold one thing, then we will see delay somewhere else. So affordances often incorporate body scale. That's important for us in our field to consider. All right, so what's the person's size relative to the environment or the task constraint that you're asking them to do? Right? My body scale changes, so my ability, the affordance, like the stairs, right? My legs get longer, my legs get stronger. My body scale changes, therefore the affordance that the stairs give me to move changes. Right? But it also means that in our job, we have to think about scaling down sports equipment, scaling down environments for games, so that people of different sizes can play and learn the motor skills, right? If I put little children, which they used to do, you know, and they turned into really great tennis players, but we want more people playing tennis, so we want more people being successful when they're younger, right? So now we change up. We have a whole youth tennis league, right? Where they play on a smaller court with a lower net and a lighter ball that bounces a lot more, so you've got more time to get there and hit it. Shorter rackets, right? So I gave you that one. What about physical education programs? What could you do? Right? What if you want to teach a basketball unit? Are you going to put your 9, 10-year-olds on a full-size basketball court?
No, we probably have to take half course.
Right, half court. Hopefully, right, here's something to think about as you move into working in this environment, right? When I look down in our gyms here in college, the basketball net hangs from the ceiling on a backboard, right? Now I understand why, because that's safer. Right? I've seen lots of injuries in gyms where the basketball net is on a post and people slam into the post and get a concussion. So I understand that that situation is safer. but they don't have it set up on any kind of a pulley system so that you could lower that basketball net to run a summer camp for young children. Right? So it always amazes me that they don't think about, they run summer camps, they've got kids here who aren't very motorically able, right, or haven't had the experience. Why don't they work out a way to drop the net down so that kids could be more successful at scoring the goal, because that's the point of the game, and then it becomes more fun, right? So what about a temporary or permanent disability? So when you go back to the visual cliff information, there's data on kids who were in a cast for some reason or another. So maybe their legs were really bowed and they had to put them in a hip-leg cast to try to straighten up their legs. And so they did not creep at 8 months like they should have done because they were in this big cast setup. So then when they come out of the cast and you put them on the visual cliff, at an age when they should be wary of the cliff, they don't understand it because they haven't had the self-locomotion experience. Right? So that would be a temporary disability. Okay? Think about, how do you develop understanding of color if you're blind from birth? Right? So if I'm blind from birth, I can get all those haptic perception characteristics of an object, but I don't know what color is. That's hard to explain color. There was a fascinating piece on the telly the other evening. Maybe it was in Trevor. No, I can't remember what program it was on. But they were talking about a friend who had been blind from birth, and she wore pink all the time, right? So she would wear a pink shirt and pink pants, and her running shoes were pink, and her jacket was pink, and oh no, I know, it was on a YouTube video I was watching, and eventually the person said to their friend, "So I'm really fascinated, what is it with the pink?" And she said, "Well, the only way I can visualize pink is it must look like the flavor of a grapefruit." So her way of understanding color was to connect it with flavor. Pretty cool. But, you don't want to have...
One quick question, Dr. Wall.
Sure, go.
I just thought about, I know this doesn't have anything to do with the color or just the characteristics we were talking about.
Mhm.
Let's say you have somebody who was born with clubbed feet.
Right?
And when they had their clubbed feet repaired, because I know you can do that, what happens after that? Because they have been adapted to not being able to use their legs or their feet for so long. Where would they begin? Where would they start? We're talking about accommodating disabilities and whatnot.
Right. So that child is going to be, if you go back to the charts where we've got a rough age for motor milestones, right? They're going to be way behind on those motor milestones. And depending upon how long they were walking with clubbed feet before they were corrected, then the brain has to learn a whole new pattern of walking. So that's going to take a lot of time. They will probably need a lot of rehab to strengthen certain muscles, because if they're walking with their feet clubbed or really turned in, then the gastrocnemius that contracts for the toe off in the walking pattern isn't going to be doing its job properly, right? Because the foot and the ankle are all in the wrong position. So there's a lot of strength and flexibility that has to be worked on that, and you're going to see very delayed movement patterns. Now, I've never worked with a child with that problem, so I don't know whether, if it is surgically corrected, do they ever get to the point where they can run what we would say typically, normally, right? I'm not sure, because I've never worked with a child with that. But yeah, that would be really interesting. Certainly a lot of delay. I just don't know enough about the surgical procedure to know if they get to a point where, for example, right, with a run, we have to see that flight phase. Do they ever achieve that flight phase? Are they able to push through their foot and their ankle enough to get off the floor, or is their running pattern really very fast walking?
Is that not a common disability to see, is clubbed feet?
It wasn't where I grew up and was teaching, I have to say. I've seen a lot of kids with very bad internal rotation of their hips, so their feet are turned in a lot, which isn't quite the same thing, and that causes a lot of problems with running. So you see some very particular running patterns with children when their feet are turned that far in, because they can't push through to go forwards. So they tend to take very short steps because they can't generate enough power. And you see quite high knee lift because the foot is in the way, right? So to clear the foot on the swinging leg, they have to lift their knee quite high. So you get this quite distinct running pattern for children that have that very turned in feet. You know, and sometimes it's only one foot that's very turned in, but even that will alter what you see, right? Does that give you some pictures in your head?
Yes, I just wasn't sure how that worked because I know it's a genetic condition, but I didn't know how rare it was or if you had seen it before.
No, I really haven't, I have to say. Not that I'm aware of, anyway. So maybe I've had children who have already been corrected when they were younger. And so I'm just not aware of it. Yeah. Now you've got me thinking now, I'm going to have to start asking that question. Okay, so deprivation can put people at risk of not just delayed movement skills, but delayed perceptual skills. All right, so they saw this when the Iron Curtain, so before your time, but when the Iron Curtain lifted up and people from the West went in to East Germany and what was the USSR and places like that, they found orphanages where there were lots of children who were kept in their baby cradle, right? And they were 6 years old, standing in a baby cradle. And it wasn't that people were trying to be unkind, but there just weren't enough workers to let the children out and keep them safe. So the safest place was to leave them in the baby bed, right, with the gates up. And so they found these like 6 and 7-year-old children whose motor skills were severely delayed because they just hadn't been able to get out and walk and run around. But it wasn't just their motor skills, it was these perceptual skills as well. So, yeah. And going back to the brain information, the more movement experience infants and toddlers and preschoolers get, then there's some, and we'll get more information about this as the imaging techniques and equipment get even more sophisticated, but there's some indication that the synaptic connections between various parts of the brain is more wired than in children that don't do a lot of physical activity. So, yeah, I think that's what I had for today. Let's see. Yes, because I want to cover postural control and balance on Thursday. I'm going to have to scoot through this and take some of these slides out so we can get finished on this. So my goal for Thursday is to look at postural control, because I think you need to go away and absorb this idea of the connection between motor action and perceptual development, and then we'll transfer it into postural control and balance scenarios. And then hopefully we'll have enough time to make a start on chapter 15. Okay, so that's my plan for Thursday. Okay. Questions? So I did put up...
Not today.
Not today. No, I like the club foot question. That's got me thinking now. I did put up a new schedule. So the next exam, we won't do chapter 13. It'll be 14, 15, and 16, I think. Okay. So that's good. One less chapter to have to review for the exam. And yeah, stay warm wherever you are. It's ridiculously cold here in Portales. If you're going out, I don't know if you guys have bad weather, but it's pretty nuts here. So be careful, wear your masks, stay safe, all that stuff. Okay? And I will, what's tomorrow? Tomorrow is Wednesday. So I haven't loaded the film from yesterday. Oh, you're going to love the film this week. We had to play indoors because it was 21 degrees yesterday, lunchtime, I think, 23 degrees. So we couldn't play outside on the playground. So we have an insane indoor session for you to watch and do your playground analysis on from yesterday. So when I wrap up here, I will go home and start to download that so that you can access that video. I haven't seen it yet, so I'm excited to watch it. Kids had a lot of fun. It was a little chaotic, but they had fun, and they did a lot of moving, so that was good. It achieved the goal. Yeah. So tomorrow, use that time to keep catching up on your playground binder. I know you asked some TGMD questions. Kayla, did I answer everything you asked?
Yes, I'll scan those documents to you later so you can see, because really the only question I had was how to properly add to get the skill score.
Okay. Okay. No problem. I can take a look at that this afternoon. I don't have any other classes today, so it's a good day for trying to catch up on grading and emails.
Sounds good, thank you.
Okay? All right. Well, have a good afternoon,
You as well.
and I'll see you on Thursday.